Hello friends, welcome again to my channel. Today I will discuss a very important, a new topic, pavement evaluation by falling weight deflectometer. And this procedure is covered in IRC code 115/2014. Structural evaluation is based on measurement of response on application of standard load. And for this, you might be knowing that Benkelman beam deflection studies have been carried out for a long time in India for measuring the rebound deflection under static load. This code was last published in 1997 based on research work done during 1984 to 1990. But the major limitations of this method is that it is unable to simulate loading conditions of moving vehicle. The procedure is labor intensive and very slow, and it does not have ability to predict properties for different constituent layers. So in Benkelman beam, what we get the response of the entire pavement, and this response is related to the requirement of overlay. Therefore, the new equipment which is used to determine the residual life of in-service pavements and overlay thickness is falling weight deflectometer. This is used worldwide, and now in India also it is being promoted. It is encouraged to use falling weight deflectometer for design of overlay on all national highways and state highways. This structure evaluation should be accompanied with pavement condition assessment, which we do in Benkelman deflection study also, in situ subgrade strength, and pavement material characterization. The concept is same as in the case of testing of any structure. That is, when you apply a load, the structure gets deflected. When you apply a load on the pavement, there is a deflection in the pavement, and this deflection is maximum below the load, and it reduces as we move away from the applied load. And this deflection will depend upon the strength of individual layer and their thicknesses. That is the concept. And therefore it follows largely the mechanistic approach. It enables the design or evaluation based on fundamental materials properties. Load pavement is dynamically simulate the actual traffic loading and loading duration. The back calculated layer moduli computed from deflection measurements are nearly representative of the field conditions. So these are unique features which are not available in Benkelman beam deflection study. Falling weight deflectometer is an impulse loading device in which a transient load is applied to the pavement by dropping a mass from a predetermined height on the pavement, and corresponding peak load and peak deflections at different radial distances are measured. Now, working principle is explained in this figure, that you have a falling mass and a loading plate, and this loading plate is provided with a rubber pad below, and we create an impulse here, and because of this falling weight, because of this impulse, the pavement gets deflected, and these deflections are measured through sensors at different locations, and this is used to draw the complete deflection bowl of the pavement. Now this FWD can be either trailer mounted or it can be vehicle mounted, but in both these the working principle remains same, that it has a loading unit which has the ability to simulate actual loading conditions, deflection units, a series of sensors which can capture deflection data at different radial distances, to draw this deflection bowl. Although in this figure only 6 sensors are shown, but it can be up to 9 also, and generally minimum of 7 sensors are required. And then we need a controlling unit which will operate the equipment and data acquisition system, and also this impulse loading device through which this transient load is applied on the pavement to measure deflection bowl. So this is what a FWD consists of. The important features of this FWD is that we can control the weight on the plate by controlling the weight of the falling mass and its height. This can be, falling mass can be from 50 to 350 kg and fall height can be from 100 to 600 millimeter. It has a circular plate of 300 millimeter diameter, a rubber pad of 5 millimeter thickness attached beneath so that the pressure is uniformly distributed. The target peak load here is 40 kilonewton plus minus 4 kilonewton, and if it is not this, then we need to make some adjustment in the deflection profile so that it represents a weight of 40 kilonewton, and the care should be that if peak deflection exceeds the sensor's measuring capacity, the target load should be reduced, and target load should be increased if deflection at radial distance of 1.2 meter is less than 10 micron. FWD should be capable to generate load pulse of 15 to 50 millisecond, which would represent time needed to traverse the length of tire imprint at a speed of 60 km per hour. And sufficient number of deflection sensors, generally 6 to 9, although there are 6 in this figure, but minimum 7 are recommended, but it can be up to 9 also to adequately capture the deflection bowl. And the sensor distance is kept like this. The first sensor is just below the load, so we call it 0, and then 1, 2, 3, 4, 5, 6 are placed at a spacing of 20, 30, 45, 60, 90, 120, and then if they are more than at 150 and 180 centimeter distance from the load. Now these are used to draw the deflection profile, and the profile will look like this. That this is the sensor just below the load, so you have the maximum deflection, and as distance varies, as you move away from the load, the deflection will reduce. So this is at 0, this is at 20, 30, 40, 60, 90 and 120 centimeter, and you will see the deflection goes down. So this deflection profile is used to determine the properties of the layers. Now, when you go for pavement evaluation, the first step is to carry out pavement condition survey. And this is to be done before start of the collection of deflection measurements. IRC 115 has given certain criteria for classification of pavement sections. It is primarily a visual observation survey to divide the total road length into homogeneous sections of either good, fair or poor condition. Now this is if the pavement has isolated cracks of less than 3 millimeter width in less than 5% area of total paved surface, and average rut depth is less than 10 millimeter, it is categorized as good. And similarly, conditions are given for fair pavement conditions and poor pavement conditions. A poor pavement condition will include wide interconnected cracking of more than 3 millimeter width in 5 to 20% area, or cracking of any type in more than 20% area, that is the failure criteria generally, and or average rut depth of more than 20 millimeter. So it is preferred when you divide the total length into homogeneous sections, it is preferred to keep length of each section at least 1 kilometer. Otherwise, sample size for deflection measurements will be changed very frequently. Now, once the road length is divided into sections, then we go for deflection measurements, and there can be different schemes for deflection measurements. That deflection can be measured along the most distressed wheel path. Deflections can be measured along inner as well as outer wheel path of the lane, or it can be measured along both wheel path of only the outermost lanes, or it can be along the more distressed wheel path of each lane. Now, in each of these cases, there are certain criteria, certain guidelines given in IRC code, that if you have single lane or two-lane two-way carriageway, then we should measure along both outer wheel path. And maximum spacing between measurements should be 60 meter in case of poor condition of the pavement, 130 meter in case of fair condition, and 500 meter in case of good condition. So in 1 kilometer length, you will have two measurements. If it is a 4-lane single carriageway, then measure along outer wheel path of outer lane. This will be the maximum spacing. If you are measuring along the outer wheel path of more distressed lane, then this should be the spacing. And if you are measuring along the center line of the paved shoulder, that is in case of widening projects, then it will be the spacing. Similarly, for 4-lane divided carriageway and for dual carriageway with 3 or more lanes in each direction. These are the maximum spacing for data measurements. In terms of lateral spacing, outer wheel path of outer lane in case of single lane, 2-lane single carriageway, it is 0.6 meter. In case of 2-lane, two-way single carriageway, it is 1 meter. And in case of divided carriageway with 2 or more lane, it is 0.75 millimeter. And the outer wheel path of inner lane is defined in case of multi-lane single carriageway as 4 meter from the outer edge of the outer lane. 4-lane divided carriageway, it is 4.2 meter, and 6-lane divided carriageway, it is 4.2 meter for central lane and 5.2 meter for median lane. And all these distances are from outer edge of outer lane. So the procedure is like this, that you mark the test point, place the load and sensor assembly on the test point, raise the mass to predetermined height so that you get a load of 40 kilonewton on the plate, drop the load and record the deflections, and record air temperature and pavement temperature, and then go to the next location. I'll show you a small video just to illustrate how it is really done. Now see here, now this is the plate and this is the weight. This weight is raised by this magnet and then it is released. And that creates an impulse here. These are the springs here which are attached to the plate and rubber pad here below the plate. Now these are the, I'll show you from a different angle. These are the sensors. These are the sensors which basically record the deflection. So this magnet raises the load, raises the mass, and then it releases. And this creates an impulse here. And deflected profile is measured by these sensors. So the first load is the seating load, and then we start measuring for second, third, fourth impulse. And that is how the data comes on the data acquisition system, that the load is 39.6 for the first impulse, and these are the deflections for D0, D1, D2 and so on up to 9th sensor, for third, for fourth. So that is how the deflection measurements are done in field. Following data should be recorded for each point: section identity, position of the lane, transverse position of the test point, measurement spacing, time of test, air temperature, pavement surface temperature, drop number, peak value of the load and deflection for each drop, load plate diameter, and number of sensors and their radial offsets. Now, steps for measuring deflection at test point: that you mark the point on the pavement, center the load plate of the FWD over the test point as I showed you in the video, lower the loading plate and displacement transducer, that is called geophones, onto the pavement, raise the mast to a known height and drop one seating load. Load and deflection data for seating load should not be recorded. Raise the mast and drop, record the load and deflection data into the computer through data acquisition system and repeat it 2 more times. And then record air temperature and pavement temperature. Now, field data which you obtain from FWD, it consists of peak load, peak deflection, and deflection at different railed locations. Now, any unrealistic data must be identified and removed. These data should be checked so that deflection should decrease with increasing distance from the loading plate. Deflection value should be not more than the capacity of the sensor. Average value of load and deflections are calculated from 3 drop test data collected, and deflections are normalized to correspond to a standard target load of 40 kN. Now, whatever measure you take, the actual load which is coming on the plate, the impulse load, is never 40 kN, and therefore the deflection profile is corrected for 40 kN. It is normalized. Linear interpolation is done. Then the layer thickness is input to the Bell calculation analysis, and you can find out the layer thickness by any method, either from historical data or by taking a core or by making a pit at the site or using GPR, ground penetration radar. But pit excavation is simplest and the most accurate method. And one thing that should be kept in mind, that location of thickness measurement and FWD testing should coincide. Now, once you get the data, then we need to process the load and deflection data. So, back calculation of layer moduli. Using this deflection profile, we make use of software to calculate the elastic modulus of different layers. Now, elastic modulus of different layers are corrected for temperature using this equation. ET1 is equal to lambda times ET2. That is the elastic modulus at temperature T1, elastic modulus at temperature T2. And lambda is 1 minus 0.238 log of T1 upon 1 minus 0.238 log of T2. Now, subgrade and subbase layers, they are affected by moisture, and therefore seasonal variation correction is applied to these layers using these equations. These are given in IRC code. Then we determine what is the design traffic, because we are designing the overlay. So for what traffic this overlay to be designed. And this is similar to what we have done in IS 37 when we were discussing in another video, a design of flexible pavement as per IS 37. This equation is same to calculate the design traffic. A is the initial traffic in the year of completion of construction period. R is the rate of growth. VDF is vehicle damage factor, and this is lane distribution factor. I have explained this in detail in my earlier session on design of flexible pavement. Now, fatigue life is the pavement is considered to have failed if there is more than 20% paved area cracked, and is the equation to calculate fatigue life given the tensile strain at the bottom of bituminous layer and modulus of the bituminous layer. For 80% reliability and 90% reliability, This equation also has been discussed quite in detail when we discussed a design of flexible pavement as per IRC 37. Rutting equation is also the same. That is for 80% reliability and 90% reliability, and that depends upon the vertical compressive strain at top of subgrade, which is calculated from the IIT PAVE software. And I explained in my earlier presentation how to run IIT PAVE software also. The overlay design can be based on any of these four methods. Subtraction of already carried traffic from initial design traffic. If you know what was the original design traffic and how much traffic has already applied on the road, then the difference will be the remaining life. Or it can be based on critical stress and strain level analysis without taking into consideration of already carried traffic. Or you can compare present layer moduli with initial expected values. Or it can also be based on correlation with the deflections and deflection bowl shape. Any of these four methods can be used to determine the requirement of overlay. But IRC suggests the use of critical stress and strain levels method to find out the requirement of overlay. So it basically uses back calculation to find out the material properties, that is E value, based on observed pavement response. And there can be several approaches, but KGPBACK software is used to calculate the elastic modulus of different layers. And input to this software are load, that is 40 kilonewton, tire pressure 0.56 MPa, how many number of deflections are measured, and what are their distances, layer thickness. For bituminous layer and granular layer, we take only two, bituminous layer and granular layer, and then subgrade. And Poisson ratio of each of these layers, and what is the modulus range for each layer, that is to be given as input parameter. Now for bituminous layer, what IRC suggests that thick layers without much cracking, the range of elastic modulus can be 750 to 3000 MPa. And for distress condition, and that is fair to poor, it can be taken 400 to 1500 MPa. The granular layer combined for sub-base and base, it can be 100 to 500 MPa. And subgrade, the E value for subgrade can be determined either by DCP test using this equation, which is given IRC code. It can be based on CBR method, or it can be based on measured deflection at a distance of 1200, 1500, 1800 mm. So we take average of these three values and put in this equation delta. P is the wheel load in Newton, mu is the Poisson ratio, and you can calculate the E value of subgrade. And the range which is to be given in the KGPBACK software is from 1.2 e value to the power 0.8 to 1.2 e to the power 1.2. And if there is no information available for E value of subgrade soil, you can safely assume 20 to 100 MPa. Now let us take one example. How do we basically determine the overlay thickness based on FWD data? Let us say this is the present composition of the pavement. That bituminous layer is 170 millimeter and granular layer is 575 millimeter. The overlay to be designed for a design traffic of 100 MSA, and these are the deflection values which are normalized to 40 kilonewton load and with 5 iterations. At 0 distance is a 0.481, at 300 0.294, and so on. And the pavement temperature at the time of test. Now these values along with these values are used in KGPBACK software to determine the E value of individual layer. So these values will be used in KGPBACK software along with pavement temperature. The total input parameters for back calculation of layer moduli will be that single load is 40,000 Newton, contact pressure 0.56 MPa, number of deflections 7, radial distances 0, 300, 600, 900 and so on, and major deflection values. These are taken the first set of data from this table, and layer thickness starting from top the 170 millimeter and 575 millimeter. These are here 170 millimeter bituminous layer and 575 millimeter granular layer, and Poisson ratio is 0.5, 0.4, 0.4, that is for subgrade third layer, and this is the range of layer moduli to start the iteration. So bituminous layer it is 750 to 3000 MPa, for granular layer it is 100 to 500 MPa, and for subgrade it is 57.2 to 83.4 MPa. Now these values are given input to KGPBACK software, and I will demonstrate to you how these values are entered and how do you get the layer moduli. So open the KGPBACK folder in your system, and here KGPBACK module. Now it will require some input data like load 40,000 Newton, pressure 0.56, how many data points you have taken, 7, what are the distances of these from the load, and then what are the values of deflections in millimeter. You input all these data, then all the data are coming from the table, previous table, and now the layer thickness is 170 for bituminous and 575 for granular. Their Poisson ratio 0.5, 0.4, 0.4, and what is the range of moduli to start the iteration. So 750 to 3000 for bituminous, 100 to 500 for granular, or 57.2 to 83.4 for subgrade. After that you wait for a while because the program is running now in the background, and once the execution is complete this screen will disappear and it will take you to the original folder. So now you open the backout folder in the notepad, and here you will get all your input data which we provided to the program, and finally the back calculated values of moduli. We got these values of layer moduli for the first iteration. Similarly you can do the second iteration, third iteration, fourth, and these are corrected now for temperature and seasonal variation. Bituminous layer E value is corrected for temperature, and E value for granular and subgrade are connected for seasonal variation, monsoon season, and I presented those equations to be used for this. So these are the final values of layer moduli. We consider 15 percentile of these values for design purpose. So finally the value coming for bituminous layer it is 1112 MPa, for granular layer it is 173, and for subgrade 44.3. Now with these values and layer thickness, it's now 3-layer pavement structure having bituminous layer, granular layer and subgrade, and we calculate what is the strain at bottom of bituminous layer and the top of subgrade layer for existing pavement. With these values of elastic modulus, we calculate what is the strain at subgrade level and strain at the bottom of bituminous layer. Let us say these are the values. And how to run IIT Pave, I explained in detail in my earlier session on design of flexible pavement. You may refer that. Now with this value of tensile strain at bottom of bituminous layer, we calculate what is the life. We calculate fatigue life using this equation where epsilon T is 284.5 micron and MR value is 1112 MPa. So we get the remaining life 11.0 MSA. from this equation, which is less than 100 MSA, and therefore it is unsafe. So we need to provide overlay. Similarly, we determine from rating criteria the vertical compressive strain at subgrade level is 439.6 micron. You put this equation, you put this value in this equation, you get remaining rating life is 233 MSA, and that is more than 100 MSA, and therefore it is safe. So the existing pavement is safe from rutting consideration, but it is not safe from fatigue consideration, and therefore we need to provide the overlay. Now let us provide the overlay, a bituminous concrete overlay of 95 millimeter with VG30 binder with elastic modulus of 1695 MPa. Now this guidance you can take from 37, IRC 37. So now it is a 4-layer system, 3 layer of existing structure plus 1 layer of overlay. So input parameter to IIT PAVE will be thickness is 95, 170 and 575. This is the new thickness of BC layer, old thickness of bituminous layer, and that is granular layer 575 millimeter. Elastic modulus like this, Poisson ratio like this, and we calculate the epsilon T, that is the tensile strain at bottom of bituminous layer 159.8, and you put this value in the equation again, and you get the remaining fatigue life of 104.4 MSA, and which is more than 100 MSA, and therefore the design is safe. And this design was already safe in rutting, and therefore there is no need to calculate this value. But if you calculate sigma V, that is epsilon V, it is 208, and this gives you a design life of 690 MSA. So the overall pavement is now safe from both consideration, failure as well as rutting. So design overlay thickness will be 95 millimeter of BC with VG30. So thanks for watching, and if you have any comment, please do write in the comment box.